Hi, in this video we're going to be talking about how to find the volume of a solid of revolution. There are two methods, so we're going to split this up into two videos, but the first method we're going to talk about is the disk method. So let's look at some motivation for this. So suppose we have a solid that's formed by rotating a region around an axis. So our region that we're going to be looking at is actually this yellow region here. And we're taking the whole region and we're rotating it around the x-axis. Okay, and what we want to do is we want to find the volume of this region. So there's two ways to do it. Okay, we can either add up small disks, so we can take it and look at little slices of it that look like disks, or we can add up small cylinders that will kind of close in on the center and give us the volume. So adding up the small disks is creatively called the disk method, and adding up the small cylinders is called the shell method, which does seem to be a bit more of a creative name until you realize that the cylinders actually form shells of our solid. So now let's take a look at the idea behind the disk method. So what we're going to do is we're going to take this solid here, and we're going to just create small little disks inside of our space, and we're going to add up all of these little disks. So let's just draw two representative disks here. And what we're going to do is we're going to add those together. So, of course, we're going to need to know what the volume of one disk is. And all it is pi r squared, so that's the surface area of one side of the disk. And then we're going to multiply it by the width of the disk. Okay, so what's r squared in our case? Well, r squared, or just r, is the distance from our axis to the function, right? So what's our r here? Maybe it's here in white. We'll start at the axis of rotation. Remember, we're rotating it around the x-axis in our case. And it goes right to the outer edge, which is f of x. Okay. So in this case, it's some f of x. And then our width, well, let's go ahead and take a look at our disk again. So our width is this small thickness of it. And so we're going to call that maybe delta x. If we were rotating around the y-axis or something parallel to the y-axis, our width would be delta y. But since we're rotating it around something parallel to the x-axis, our width is going to be delta x. Okay, so now let's go ahead and say that the volume of the solid is actually equal to the sum of the volume of the disks. Right, so that's going to be the sum of f of x sub I squared, remember this is r, times the width, which is delta x, and then we'll just take that pi because it's a constant and pull it on the outside of the sum. So we get our formulas here. As you can see, being hinted in the bottom left of the screen, the volume of the solid, well, I guess, was approximately that, but then we take the limit as our thicknesses get smaller and smaller, and as you remember, that turns the summation into an integral. So we get the integral from a to b, where those are our bounds of the solid, or the region that we're rotating around. We can pull that pi on the outside still, and it's just going to be f of x squared dx. And so that's our formulas here. Volume is pi times the integral of a to b of f of x squared dx if we're rotating it around some axis parallel to the x-axis. And if we're rotating it around some axis parallel to the y-axis, it's going to be in terms of y. So it's going to be pi integral of some function g of y squared dy. So the hard part in these is finding out what is f of x and what is g of y. So let's look at our first example. We want to find the volume of the solid formed by rotating the region bounded by y equals the square root of x, y equals 0, and x equals 4. And we're going to rotate that around the x-axis. So we're going to rotate it like so. So the first step is we're just going to graph it. So if we look at a graph of it, which is the best way to handle these situations because they are very visual and we'll easily be able to pick out what our f of x is going to be. So the square root of x looks something like this, the top half of a parabola. Y equals 0 is the x-axis. So let's label that in red. And x equals 4 is going to be this vertical line at 4. So let's go ahead and label everything. Y equals the square root of x. So which region are we taking and rotating it? So we're going to rotate this highlighted region here around our x-axis. Right, so we're rotating it around this axis here. Okay, so now we need to find f of x and our bounds. Right, because we're rotating around a parallel axis to the x-axis, we're going to be dealing with dx's. So f of x is going to be the distance from our axis of rotation all the way up to our outermost part of the region. Okay, and that tells us that f of x is just going to be the square root of x. So let's go ahead and highlight that. And now for our bounds, well, we know that the region starts over here at the origin and it ends at x equals 4. So our bounds are going to be x equals 0 is going to be a, and b is going to be x equals 4. So now we can just set up our integral. So we're going to step 3, set up the integral, and evaluate. Okay, so we get the integral from 0 to 4 of f of x, so that's the square root of x, squared, dx, and we're just going to stick that pi on the outside of the integral. So this is equal to the integral, put that pi on the outside, 0 to 4 of x dx. The integral of x dx is going to be x squared over 2. Put that pi on the outside and we evaluate from 0 to 4. Okay, so we get pi 4 squared over 2 minus 0 squared over 2, which is going to be pi times 16 over 2, or 8 pi. And this guy here is our final answer. For our next example, let's find the volume of the solid formed by rotating the region bounded by, and let's just start by going ahead and graphing everything as we come across it. So x squared minus 2x and y equals x. So y equals x is pretty easy. There it is. And then let's extend it a little bit just in case. And y equals x squared minus 2x. So we're going to have to find the vertex of this somehow. We could either do negative b over 2a comma f of negative b over 2a, or we can complete the square and put it into a standard form. So let's go ahead and remind ourselves how to do that and put it in standard form. Okay, so we have y equals x squared minus 2x. What we're going to do is we're going to divide this by 2. So we take negative 2, divide it by 2, and square it. And then we're going to add and subtract it. So we're going to say y is equal to x squared minus 2x plus 1 minus 1. Or y is equal to x minus 1 squared minus 1. So that tells us we shift to the left, we shift to the right one, and then we go down one. So this is our vertex. And remember, it's a positive x minus 1 squared, so it's going to open up this way and open up this way. And now we have a sketch of our graph. So what we're going to do is we're going to rotate this region here about the line y equals 4. So we have a line up here, that's y equals 4, and we're going to be rotating it around this axis. So since it's parallel to the x-axis, we're going to be dealing with dx's again. So fortunately, we are already in forms where y is equal to a function of x, and we don't actually need to do any manipulation here. So let's go ahead and let's find f of x. So f of x is going to be a little bit trickier to find this time, mostly because we're rotating around something that's not a standard x or y axis. But we can handle this like we do with every other math problem. The hard part is setting it up and not evaluating the integral. So let's walk through the hard part. So if I am looking to rotate this highlighted region, what I'm going to do is I'm going to see what's the distance between here, the axis that we're rotating, and here. So the first part for our f of x is going to be 4 minus, because to get from this point to any other point, it's going to be 4 minus y. And our y for our outer one is going to be this parabola here. So it's going to be 4 minus our parabola, and let's write it as 4 minus x squared minus 2x. And then what we're going to have to do is we don't have a solid thing that lies right on the axis. So instead of looking like a disc, it looks more like a washer or a CD. So we're taking the outer one and we're going to subtract the inner one. So this is our outer radius, and our inner radius is going to be, let's say, g of x, which is going to be 4 minus x. Remember, the distance between this axis and our point here is going to be 4 minus y, and y in this case is x. So what we have is we have two separate integrals to find the volume. We're going to integrate from a to b. We haven't found those yet, but we will. Of f of x dx minus the integral from a to b of g of x dx. And remember, it's pi times the radius squared, so we're going to subtract pi times the radius squared. We can bring that all inside again because integrals are linear. So we get pi, we can factor that out. The integral from a to b of f of x squared minus g of x squared dx. And this is our generalized form for the integral using what's called the washer method so creatively because it looks like a washer. Now, let's find a and b. So to find a and b, they're not given to us. So we're going to have to find them ourselves. And let's look back at our graph. We know that the region starts where they intersect and it ends where they intersect. So let's go ahead and find the intersection. So we're going to find the intersection point. And to do that, we're going to set x equal to x squared minus 2x. So subtracting x from both sides, we get x squared minus 3x equals 0. So x is going to be 0, and x is going to be 3. And this guy is our a, 0, and the 3 is our b. So after setting up our integral by plugging in a, b, f, and g, we get pi times the integral from 0 to 3 of 4 minus x squared minus 2x, all squared, minus 4 minus x squared dx. So let's go ahead and multiply it all out, and when we do, we get x to the 4th minus 4x cubed minus 5x squared plus 24x dx. Evaluating, we get pi 1/5 x cubed minus x to the 4th minus 5/3 x cubed, or, well, I made a little mistake, that should be x to the 5th, right? And then plus 12x squared. And we're evaluating from 0 to 3. Now, when we plug in 0, we get 0. So all we really care about is when we plug in 3, and when we do that, we get 153 over 5, and we'll just stick that pi on the outside there. And that is the volume of our solid. Thank you for watching.